Alright guys, so this morning we're going to take a look at the limit of a function, okay, which I believe you would have already seen in the for you functions, okay, if I'm not mistaken. Or at the very least you would have looked at expressions where and behavior of expressions around particular x values, which exactly is exactly what a limit is. Okay, so I took the liberty of doing this in advance here. I just graphed the function in number 1 on the grid provided there, okay? And then number 2 asks us to use the graph to evaluate the following limit, right? And so we want to look at the limit as x approaches 3. Okay, so we want to look at the behavior of the graph around the x value of 3. Well, if I were to take a look at, like let's say I want to evaluate where the graph is from the left side of 3, which we denote as being like the minus, right? We want to look at what is the actual y value when I look at the limit from the left side. So that just simply means I'm coming from the left until I approach an x value of 3. Oh, it looks like right here, the y value there, as I approach an x value of 3, I'm going to see that the y value is, or the limit is, 2. And if I do that again, right, so there you go, you can write that down. And then we can say, okay, well, what if I approach this graph 3 from the right, right? Okay, so I'm coming from the 3 from the right. What do I get? Oh, I get the same value, right? So f of x is continuous and exists and has a value of 2. Because the limit matches from both sides of the particular x value, it's continuous at that point, and the limit also exists. Okay? So we can actually find what that limit is. And then if I were to use what we're going to call the direct substitution technique later on in the next question, right, I can actually look at what happens when x approaches 3, not from the right or not from the left, but 3 right on of the function, right? You can say, okay, well, we're just going to substitute the limit right in there, right? So we know what the function is going to be as x approaches 3, of 2x minus 4. You're going to evaluate by taking and seeing what happens when you actually plug that in there, right? Don't forget your equal signs as well. Okay, and so we're going to see that it's 2 times 3 minus 4, 2. Okay, and so we can evaluate these things algebraically, or we can produce the graphs and look at the limit, because sometimes the graphs tell a bit of a better story than the function itself. Okay, sometimes you can't see discontinuities in the graph. Okay, so example 1 here just wants us to get some practice with the direct substitution, which isn't anything too crazy. We want to find the limit of this function as x approaches -1. Okay, and so we're just going to plug in -1 in for x. Okay, and don't forget your equal signs. I always forget my equal signs. Okay, if we do the math on that, we're going to see that that's going to equal -7. Okay, and then on the part B here, we just want to evaluate. Okay, well, let's go. That's going to equal -4 over 2 plus 4, which will equal -2/3. Okay, and then so the last one here, direct substitution, we're just going to plug in a limit as x approaches 3 from the right, but we're really just going to plug in the x value of 3. And so we're just going to take 3 squared minus 9 square rooted, which is 0. Okay, that just simply means that the graph approaches 0 when you're coming from the right, approaching 3. Okay. Now, we're going to take a look at some more interesting questions here, right? These are what we call piecewise functions. And we're going to use this notion of one-sided limits to help us deduce whether or not something is continuous at a particular x value, okay? And so in the box here, we have a series of generalizations, if you will. And it says that if the limit, as we approach an x value from the left, okay, so much like up above here, like let's say we were approaching 3 from the left, if the limit does not equal the limit as x approaches that same number from the right, then the limit does not exist. Okay, that means that there's a break in the graph. It's not continuous. There's a hole. Something has happened at that particular value, and we're going to see what that actually looks like with this example. Okay, however, this here would be what we saw in the first question, right? Where, you know, as x approached 3 from the left, the limit was equal to the limit as x approached 3 from the right in that first question, and then the limit did exist, okay, and so we were good. What we're going to see here when I graph this, I'm just going to graph this piecewise function, we're going to see some interesting things happen, okay? Now, there's a couple things in here you have to remember, okay, or recall or learn, okay? When I graph these piecewise functions, okay, this one's kind of nice. It's just a couple lines, and in the middle, we have a point. Okay, and then what they like to do is say, okay, well, here's x values less than 1, x values greater than 1. And then in the middle, you know, they put x equals 1. Okay, so it looks like they've covered their basis with the stuff highlighted in red here, right? Like it looks like they've made this graph continuous, but sometimes you can plot these. So well, sometimes you're always going to plot these things, these piecewise functions. You're going to see at that particular x value, in this case 1, what's actually going on, right? And so we're going to check what the limit actually is for this. Okay, so first things first, I would graph each of these individually, right? So I'd graph x minus 1, okay? But the catch is it has to be less than, and it also does not say less than or equal to. Okay, so we denote that on the graph differently. Okay, so the very first point here, x is less than 1, so I go find my x value, and it's, well, why don't we just plot this like a normal graph? We'll go say, we'll find negative 1, because that's its y-intercept, and its slope is positive 1. So I'm going to go up 1, right 1. Okay, but the catch is, this point doesn't actually exist because it did not say less than or equal to. It said less than. Okay, so it doesn't actually include that point. And so how do we denote that on the graph? Well, we denote it with what we call a hole. It means that everything up until 1, so even like 0.99999 would be a filled in dot. But as soon as you hit an x value of 1, it becomes an open dot. Okay, and so we plot the rest of the graph backwards here, right? And we get the idea. Okay, so there's the first piece of our graph. And then it told us, well, when the function is actually equal to 1, and this is the kind of confusing part, it looks like we've covered our basis with this idea of all these ones here, but really, when x equals 1, we get a y value of 1, which means the point is going to be right here. Okay, and then we plot the last one, right? So that's okay, we're done with that piece of the graph now, this piecewise function. And the last part is we're going to plot x plus 1. If x is greater than, not equal to, just greater than 1, which means we're going to have a hole again. Okay, so we can plot. We know, you know, the graph isn't actually going to be here, but we can use it to help us plot, right? So we know it has a y-intercept. We can erase it after. A y-intercept of 1, right? And then we're going to have a slope of 1. But the catch is, again, be careful, because x has to be greater than 1, right? Which means right here, this value here is going to be a hole. Okay, so you guys can plot, you can use the y-intercept to create your graph. Okay, but the catch is you can't leave that there, right? Because that's a point that it's saying is not allowed. Has to be greater than 1. Okay, so this in itself, what we've just produced here is what we would call, and it would be an example of a piecewise function. Okay, and then so we want to check, we want to ultimately find, what is the limit as x approaches 1? That's the question we're after, right? So we can check this using one-sided limits. That's what we're doing, right? We're checking from the left and checking from the right. So if we were to check the limit as we approach the graph from the left side, right, coming in from the left, I'm going to approach 1 from the left. Oh, what value would I get? Well, it approaches the value of 0. Okay, but then if I take a look at what the actual x, or like what the limit of the function is from the right side, right, that's what the plus side is denoting, well, I'm going to see something different, right? And maybe I'll highlight this so you guys can see the limit. This is all red, and then we'll do this in blue or something. Okay, we want to check from the right. Oh, we're going to come from the right side. What's the limit here? Oh, the limit here is going to be 2. Well, these two things are not equal, right? These two numbers don't equal each other, right? Which must mean that something has happened with the graph. Okay, and so we can say, based on the rules above here, that when the limit does not equal, or when the limit on the left does not equal the limit on the right, we know that this function, the limit as x approaches 1 does not exist. Okay, and then so we'll say down here, this is what we would call, like, let's say there's a jump. In the graph at x equals 1. Okay. Okay, and so if we were to actually, this is what we actually said we were going to use the graph, right? That's what we did. And sometimes the piecewise functions is a little bit easier to use the graph from the standpoint of exactly, like, I mean, so I suppose they're going to tell you what the limit, like where they're interested in, where the limit is, and you could solve these things algebraically. But sometimes it's nice to see, like, if I asked you maybe to tell me what kind of like if it's a jump or if it's a break or is it a vertical asymptote. Like sometimes you need to you got to tell me, right? It's just good to know what the graph actually looks like sometimes. Okay, so we could actually do this by plugging in the x values. Okay, so if I take a look at what happens when I approach 1 from the left, well, if I'm approaching from the left, that means I'm dealing with this equation, right? Because all the x values are less than 1, and so I'm going to go. This is going to be equal to the limit of x approaches 1 from the left of x minus 1, right? Because this was the portion of the graph that was dealing with the negative side. Okay, so you just plug it in. Well, you evaluate and you see that this is equal to 0, which is what we found on the graph. And then if I take a look at the limit here, well, this is dealing with all of the graph coming from the right side, right? And so the right side of this graph dealt with this part of the piecewise function. And so we're going to see that's the limit as x approaches 1 from the right, and that is going to be x plus 1. That's going to equal 2. Okay, these two things are not equal, right? And so again, we draw the same conclusion that the limit as x approaches 1, not from the left or the right, but as x is approaching 1, the graph does not exist because there's a jump there. Okay, so I'm going to stop here. Below here, I'm just going to jump over this. I'll show you that it's here. This is some key concepts that you guys can have a read through in terms of limits and some of their properties. In the next video, we'll have a look at doing these questions down here. Okay, so that's the first part of this morning lesson.